Hey everyone, it's section 2 in unit 1, so we're still talking about the atom. Now we're going to dive a little bit deeper into isotopes and definitely talk about how you calculate average atomic mass from all of the isotopes that exist on Earth. So, review, isotopes are formed when atom loses or gain a neutron. If it gains neutrons, then the mass goes up from what it normally would be. If it loses neutrons, the mass would go down. So over here in the image, you have carbon-12, that's traditional carbon, or the carbon atom, which we are most familiar with. That makes up most of the carbon on the planet. And then we also have carbon-14. There is such a thing as carbon-13 and carbon-11, but these are the only two we're talking about. So remember when we look at this, we should recognize that if we're talking about carbon-14 or C14, this of course is the symbol. This is the mass number, okay, which is just my protons plus my neutrons. So that value, carbon-14 or carbon-12 or whatever, tells us the element, what element it is, and what the mass number of that particular isotope is. So the average atomic mass is, as we mentioned, the weighted average of the masses of all the naturally occurring isotopes of that element. So carbon comes in carbon 11, 12, 13, and 14. Okay, so those are the 4 possible carbons that exist out there. Now, they all have 6 protons, so they're all carbon. So that's pretty straightforward. If you were to change the number of protons, that would change what the element actually was. So we know it's carbon if it has 6 protons. So everything in the universe that has 6 protons is carbon. Some carbons have 6 protons and 6 neutrons. Some have 6 protons and 5 neutrons. Some have 6 protons and 7 neutrons. Some have 6 protons and 8 neutrons. So the number of neutrons can change, and that changes the overall mass of that particular isotope. Well, what we need to do when we calculate the average atomic mass is not just take 11, 12, 13, 14 and average it, because that's not fair, okay? If you were to look at your grades, you may be happy with this. If you were to look at your grades and every single assignment was the exact same amount of points, including tests, and all that was just added together and divided by the total, and that was your average, maybe your average would be higher, maybe your average would be lower, but it wouldn't really be indicative of how much work you've actually put in, because you put in a lot more work to your tests and projects and things like that, so they're worth more points. And so that's kind of the idea behind the weighted average. If we're looking at it, what we need to include is how common are they? What percent of the total carbons on Earth are carbon-12, carbon-11, 13, and 14, okay? So it factors in that percent abundance, and you're going to see kind of how that works on one of the following slides. So as mentioned, these are both lithium. These pictures, well, I didn't mention it, but I'm mentioning it now. We know they're both lithium because they both have 3 protons. That is what tells us automatically that it is lithium. The neutrons, well, they can change. They can go up, they can go down. Even electrons, we know, can go up and go down. But either way, as long as the protons stay the same, it's lithium. Right? So on the right we have lithium-6, on the left we have lithium-7. So what that means is that on the left we have 3 protons and 4 neutrons. I'm writing it even though it's right there. And on the right it is 3 protons and 3 neutrons. Okay? So that means that the one on the left has 1 more neutron. Well, sometimes that can make it unstable. And you guys were working with the Build on Atom activity, so you got the opportunity to see that it can become unstable if there's too many or too few neutrons. Well, if they become unstable, what they do is they decay, okay? And that means that they're going to release particles or energy. Okay? And the reason they do that is they're going to release those particles or energy so that they can get to a state where they are more comfortable. Okay? Now, those particles can come in a variety of different forms, and when we look later in the year and we look at nuclear energy, you're going to look at the types of particles that are released when an isotope's nucleus is unstable. But for right now, I just want you to recognize that decay is basically when particles or energy are being released from a nucleus because of instability. Every isotope isn't unstable, so make sure you're kind of putting that in the back of your head. Some are unstable, some are stable. Some isotopes of uranium are just metal. They just sit there. Other isotopes are releasing horribly damaging gamma radiation or energy. So it just depends on the ratio of protons to neutrons that can make it slightly unstable. Yay, we're back to math. I bet you missed it. Yeah. All right. So average atomic mass is calculated by multiplying each isotope's mass by the percent abundance and then adding it all up. Okay. So I'm going to show you in just a moment how we actually do that. So this is essentially the formula, although I don't like calling it a formula because it's not something that you need to memorize a formula for, but we do want to practice the skill of adding together this weighted average, okay? So what you would do is you would take the mass of the first isotope. So looking at this example at the bottom, the first isotope is carbon-12, the mass being 12.000, meaning is exactly 6 protons and exactly 6 neutrons, okay? I then am going to multiply it by the decimal of the percent abundance. So percent abundance is 98.90. If I basically divide that by 100, then I get that it is 0.9890. Okay, so that's what I'm meaning. You multiply a decimal by 100 to make it into a percent. So to get it back to a decimal, just divide it by 100. Okay, move your decimal 2 times to the left. The bottom one will be the same, divide by 100, and we will get a decimal of 0.0110. Okay, move our decimal 2 times to the left. So you basically will take the mass of the isotope, which is 12.001 for the first isotope. You multiply it by the decimal of percent abundance, and then you're going to add that to the second one. Okay, so give me 1 second to pause, clear the screen, and then I'll show you how to set that one up. Okay, so I moved stuff around, so now I have room to work out the problem so you guys can see it. So what we would end up doing is to calculate the average atomic mass, of carbon. We would take the first mass, which is 12.000, multiply it by the decimal for that abundance, so 0.9890, plus the other isotope, 13.003, times 0.0110. If I had another one, I would say plus, but I don't, so I would be done. All right, so I'm going to put this in my calculator. Probably should have done it before I did this so that you guys didn't hear all the buttons and everything. All right, so this is 11.8968. Nope, that's a lie. 11.868 plus the other one, 13.003 times 0.0110. This one is 0.143033. Okay. I don't know why I left such a huge gap there. This is why I don't do math in front of people. All right. So then I add those two together. 0.868 plus 0.143033. That gives me a value of 12.011033. Okay. Now, looking at the problem, I would probably try to sig fig it, although this one's kind of weird. At minimum, I would not have any mass that was greater than the number of sig figs of the masses I started with. So that would be 12.011, and that would be in AMUs. Okay, because atomic mass unit is the mass, or is the unit that you use for mass. So along the way, I do want to make a point about this second area right here where I wrote down these numbers. I did not round these, so be very careful when you're doing this. You don't want to round them before it's too soon. When you're doing a calculation, write out everything and then keep going. The other way, of course, to do it would be that you could be smart about it, put it into your calculator all at once. As long as you're using parentheses around the two things that you're trying to add, then it'll understand how to do order of operations and you should be set. Okay, for these two, what I would like for you to do is I'm going to do the first one, and then I'm going to ask you guys to run through the second one on your own, okay? And then I'll put the answer down here as well. So for the first one, it says naturally occurring chlorine consists of 75% chlorine-35 and 25% chlorine-37. Well, we're not actually given detailed masses here, but we're going to just use the mass numbers that we have, okay? So again, average atomic mass is the first mass, which is 35 35 times the decimal percent abundance, 0.7500, plus 37 times 0.2500. Okay, so I'm going to put that in my calculator. 35 times 0.7500 plus 37 times 0.2500, and I get a value of 35.5. Okay, check my sig figs. It looks like I should have two-ish. I'm just going to leave it how it is, okay? For most of these, when we're sig figging these, we should be looking at the values we're given in the problem. These mass numbers are not great examples of numbers you're given in the problem, but if we were to round it to the correct number of sig figs, which those are 2 sig figs, meaning that would be the ones, then this would be a mass of about 36 AMUs, okay? 35, 36, pretty close, all right? I'm going to pause this, calculate the second one, put the answer down there, and then I want you guys to try that one on your own, okay? Okay, so you should pause now, run through question number 2, see if you get the answer I get, and then I will show you on the next slide how I did both of them if you need to see that again, okay? Are you pausing? Okay, for question number 2, I got that the average atomic mass of this unknown isotope to be 13.6, check my sig figs, 3333, so I'm going to stick with 3 AMUs, okay? 13.6 AMUs. Here's the work for both of these, so if you'd like to see them worked out again, you're more than welcome to. Again, if I do my sig figs correctly on this one, it really should be 36, so whenever I get mad at you for making an error on sig figs, then you can just remind me that I made an error on sig figs in a video, and I can't take that back because it's recorded forever. And there you go, all right? So that really should be 36 for the first one, and then the second one, 13.6. All right, so for your summary, on your paper it says reread your notes from today and summarize them in 2 or more sentences. What I would like for you to do is make that a little bit more specific. Discuss what makes isotopes different from neutral atoms, and then discuss how they ultimately give rise to the calculation for average atomic mass. All right? Run through your practice problems. And then we will be in class, and we're going to start with going through those practice problems. Please have answers to check, okay? Even if they're not perfect and you're not confident, that's okay. Have answers to check so that we will have that to go over at the beginning of class. All right, have a wonderful time.